Okay, so today we're graphing exponential functions. We're going to graph exponential growth and decay, and then we're going to go back into identifying some domains and ranges, and then this might be a new word for you. So every exponential function has something called an asymptote. It is a line on the graph that the graph gets closer to over time. And when we are graphing these exponential functions, generally you'll see the y equals b to the power of x. Another form is y equals a times b to the x. So b is going to be your base. X is the exponent, which is always going to be a variable in an exponential function. And then a is the initial value, which is the y-intercept. The next question asks you what types of situations would an exponential function model. Okay, so exponential is a situation where the increase or the decrease starts off slowly and then it gets very large very quickly. Okay, I'm going to show you, I'm going to put a couple of graphs on the board. And then I'm going to give you a minute, and I want you to talk with the people in your row or at your table. And I want you to try to come up with two situations that might follow an exponential model. Okay, so you can go ahead and you can talk to your table as you think that out. Yeah.
I don't have a job. Yeah.
All right, I heard a few good things here. Evelyn, will you tell me what your table was talking about? Okay, yeah. So different interest models. Maybe that's something you guys have talked about in another class, AP Macro or Econ. Okay, so the interest values. Okay, bank accounts. All right, who has another one? What's something else that can grow very quickly over time? Yeah, Noah? Oh yeah, great. We do actually several examples with bacteria. Okay, so multiplies quickly. That would be a good one for growth. What else? Yes, nice. Okay, population growth or decay, just depending. Okay, all right, that's a good list. Did you guys put anything else? Anything else in the line of money? Look at the stock market. Get that in there. That'd be a good one. Okay, stock values. What about, do you guys do any other science applications? Bacteria is a good one. Have you guys talked about like the half-life in any of your classes? Yeah. Were you going to say something else?
Yeah.
Yes. Half-life. We'll talk about some of that as well. Okay, so when you have these growth models, sometimes it is easier to do a model for if something doubles. Okay, so if something doubles, you can just say it's y equals 2 to the x. Your base is going to be 2. You could create an equation for that. And then if it triples, it would be y equals 3 to the x. If you did your half-life, it would be y equals 1/2 to the x. Okay, nice job there. All right. and then we are going to graph this given function and then identify the domain and the range. Okay, this first one we're going to do without our calculator, and then as we get into some more complicated examples, we will use our calculator. So we have y equals 2 to the x, okay? We are going to make a table, so you're going to make tables for your graphs. Yes, we can do it. Grab the builder, you can fix it. Okay, so if you are plugging in these values, okay, if you have a negative exponent, so if you do 2 to the negative 2, we just studied exponents. How would I rewrite that? 2 to the negative second would be the equivalent to what? Yes, 1 over 2 squared. Great. Okay, so this is going to be 1/4. Okay, so I want you to go through, I want you to evaluate each one of these. Okay, put your solutions there. And then you can go ahead and put those points on your graph. Okay, so I want you to use mental math to evaluate those. Alright, so it looks like we're doing a nice job here. 2 to the 0 is that special property. You guys did a nice job remembering that. Okay, and the reason why I went out to 3 is because if you don't, you're not going to get as good of a graph here. Okay, so some of these you are going to be estimating, so the 1/4 is very close. Okay, and then you have the half, and then you have the 1, 2. Okay, now the graph does not stop here. As you keep going in the negative direction, you're always going to be getting fractions. So what it does is it follows this line, and so you need to put your arrow on your graph. So you should have an arrow going up and an arrow here. So I want you to just take a moment and add that now. Okay, and then we're going to do the domain and the range. So the domain, our restrictions are still the same. Do you have a radical? Do you have a fraction? Okay, we do not have a radical or a fraction, which means your domain is all real numbers. And for these, I'm going to do that in set builder notation. Okay, so it's x such that x is an element in the real number set. Okay, now for your range, that's your y values. So you just have to look and see. All of your values are above what y value? 0, okay? So this is going to be y is greater than 0. Do you guys know why it's not equal to 0? It's never going to reach 0 because what's happening with all those negatives? It's becoming a smaller and smaller fraction. Okay, and that is why we have something special for the exponential functions. Okay, and that is called an asymptote. Fun word. Okay, and it is a line that the graph approaches. Okay, so it's a line the graph approaches as the value of x gets a very large or very small. Now, a lot of times these are on the axis, so I'm going to have you use a highlighter, okay, to draw these on our graphs today. So an exponential function has a horizontal asymptote that the graph will never cross. This is only true for exponential functions where it will never cross it. And the asymptote is represented by a dashed line. So you don't make it solid because it's not part of the graph, it's in addition to that. Okay, so it's a dashed line that you're going to put on your graph. And the last question says, what's the horizontal asymptote for the parent function? It's y equals 2 to the x, that's our parent function, and then label it above. So this is the parent function. Okay, so the number that it's approaching, it's getting closer and closer to 0. So your asymptote is y equals 0. Okay, now this is a line. So this is similar to the axis of symmetry where you're going to have an equation. So you have to have y equals, not just 0. The y equals indicates that you have a horizontal line. Okay, so we're going to use the highlighter so that we can see that dash. And then we're also just going to label that on our graph. Okay, so we have a dash line. We have it labeled. Okay, and then we're using a highlighter so that we can see it on the axis. Okay, or if you have a marker, that's fine too. And if you need a final highlighter, I have some over there, you can help yourself. Alright, so with our growth and decay models, we can see if the function is approaching a very large positive value or a very large negative value. So if you have exponential growth, this means that your base value is going to be greater than 1. Okay, and it's really the absolute value of it. Like if it's a negative, it doesn't count. Okay, so the absolute value of b is going to be greater than 1. If it is 1, then it will end up being a straight line because 1 to any power is what? Yep. So you would just get a whole bunch of 1s. It would be constant. So we're going to draw 2 examples of exponential growth. Okay, so like I said earlier, exponential growth can be in a positive direction or in a negative direction. Okay, so over time, it can grow upward, like hopefully our bank accounts. Okay, but sometimes it can grow in a negative direction, like the national debt. Okay, so you can have something that grows negatively. Or if you don't pay off your credit card bill, and it just keeps going up. Okay, now for exponential decay, it's the same formula. It's just your value of b is going to be different. So it's your same exponential formula, but this is where b or the absolute value of b, is in between 1 and 0. Okay, so we just talked about, oh, it can't be 1 because then it would be a constant. Okay, so if this happens, then instead of approaching infinity or negative infinity, you're going to be approaching the axis. Okay, so we're going to do 2 examples of that as well. Okay, so you could start with a positive value and get closer and closer to 0. Or you can start with a negative value and approach 0. Okay, so a few different forms of growth, a few different forms of decay. So if you're looking at the graph, you can determine if it's growth or decay. Is it approaching a very large value, a very small value for growth, or is it getting closer and closer to an axis here? Okay, you can also determine if it is growth or decay based on your function. So I'm going to give you some functions, and I want you to decide if they're growth or decay. Okay, so the first one is y equals negative 2 times 2 to the x. The second one is f of x equals 1/5 pi fourths to the x plus 2. And c is g of x equals 3/4 x minus 2. Okay, so I want you to do this without graphing. Okay, so the first thing I would do is I would see if you can identify what your base is. If you can find your base, then you should be able to say if it's growth or decay. Okay, if all you can do is label what your base is for each, then do that. Okay, so I want you to say what B is for each. What's your base? Okay, so I want you to write it down so I can see it. Okay, so write down what your base is for each. So B equals, B equals, B equals. Okay, and if you're confident in your answer for your base, okay, go ahead and label it growth or decay. And if you want to talk to somebody next to you just to make sure before you write it down, that's fine too.
Oh, that is a base. So it's number 4.
Alright, Cam, what'd you get for your base for A?
I got 2.
Good, and then so because it's 2, what did you decide it was? Nice. Okay, so this one should be growth. All right, and then James, what did you get for the base for B? Say it again. There you go. Okay, yep. So 5/4. Okay, so based on that, is it going to be growth or decay? Great. Okay, so this is greater than 1. 5/4 is greater than 1, so that's going to be growth as well. All right, and then Ryan, what's your base for C?
3.
Yep, 3/4, and then so would that be growth or decay? Please say it again. Yes. Okay, so if you're having trouble finding your base, remember, this is our model, right? So the base is always attached to x. You don't want to multiply anything together because this is going to be your A value and you have to follow your order of operations. So exponents before you can multiply. So you would not be able to multiply those until you evaluate your exponent. Okay? All right, let's flip it over for some graphing. Okay, so we're going to graph these functions. Okay, we are going to find the domain, range, y-intercept, and asymptote. Okay, so we're going to find all of those, and then we are going to do the end behavior. Okay, for every problem on your homework, I mean, I can do the question on that one.
Yeah, I need it.
Okay. Yeah, what's up?
When are you multiplying?
When will you end up multiplying these together?
Yeah.
So when you're graphing, we're going to be plugging values in.
Okay. So
like we did here, where you're substituting in your x, you multiply after you plug in your value for x. Okay? So we are going to be doing that here, but I'm also going to let you use your graphing calculator. Okay, so for A, you have f of x equals 10 3/4 x. Okay, and I want you to have at least 5 on your table that you've written down. Okay, and then with your graphing calculator, we're going to go ahead and we're going to plug that into y equals. Just so you know, if you use the fraction button, it will give you the result as a fraction, which you may or may not like because when you are graphing, it's easier sometimes to estimate a decimal when you're graphing.
What decimal?
So when we're doing an estimate, okay, on your graphs, you only have to worry about going to the nearest tenth. Oh, let me change my window. Actually, that's a really nice window for it, but that's probably not what you guys are going to see at first. Okay, when you're looking at your table, okay, you're going to have some decimals, and we're not going to be able to tell the difference between 13.3 and 13.34. Okay, we just aren't going to be that precise. They're going to be estimates. So when you round, you can round to the nearest 10. If I'm just looking at this graph, a 10 by 10, this isn't as nice of a picture as you could see that one that we had before. So when you're looking at your table, you're going to look past that 10 by 10 window. Okay, so we're going to go to our table. And sometimes you might have to scale your graph by something different, and that's fine. Okay, so if I'm looking here, I can start to see these values are getting smaller, smaller, and smaller. Okay, so I'm just going to write 8 is 1. 5 is going to be 2.4. And my goal is just to get as nice of a graph as possible. So you might not have all of these exact points. 1 is 7.5, so that's going to be a nice one to graph. 0 is 10. And then maybe I would just skip some here, like negative 2, 17.8, negative 3, 28.7. Okay, and then I can go by ones on the x-axis, okay, but my y's, I do want to bring those up kind of close to there, okay, maybe I would stop at negative 3 or pretty close to it. So let's see, if I went by 3's, that would get me to 30, okay, and that would be your 31.6, that could be a little bit past that. So I think that's what I'm going to do. I'm going to go by 3's. So 6, 9, 12, 13, 18, 21, 24, 27. Okay, and then we are going to plot those points. That's just a little bit above 30, so that's fine. When you're doing this, you should end up with a exponential shape. Okay, it's going to be closer and closer to 0, and then make sure you put your arrow on both sides. Okay, so double check that, make sure you have an arrow at the top, an arrow at the bottom, and then once you graph, I want you to go through and find everything that it's asking you. So your domain, your range, your y-intercept, your asymptote, and we are going to put that on the graph, and then your end behavior. Okay, so the really nice thing about exponential functions, your domain is always going to be all real numbers. Okay, and then your range, for this one, everything is still above 0, so it's y such that y is greater than 0. Okay, in this case, we did put the intercept on our table, so it's just 0, 10. Okay, and then the asymptote is y equals 0. We're going to go ahead and put that on our graph. Okay, so you are going to have to label your asymptote y equals 0. Okay, and then if you need a refresher on that end behavior, remember you say what happens on the left, what happens on the right. So as x goes to negative infinity, where does f of x go? And as x goes to infinity, where does f of x go? Okay, so this is going to be a little bit different. So on the left side, you can see it's going up. Okay. So on this side, it's going to be going to infinity. Okay. On the right, it's not going to negative infinity. It's getting closer and closer to what number? 0. 0. So you're going to approach 0. Okay.
Do we say that to the asymptote every time?
If it is 0, yes.
So if it's like -2.
Okay, then if it's -2, then what's it going to approach?
-2.
Yep, so then that's what you put. Yeah. All right. Okay, and then for part B, again, you can go ahead and plug that into your calculator. And what I think would be helpful for you to practice is looking at the table and you start coming up with what points you want to include. Okay, so you have to have at least 5. You're welcome to have more than that. Sometimes I like to write down more just so I can organize. That helps me organize. Okay, so plug it in and then you're going to decide what you want to plot there. So what number has the exponent? What number is that exponent? Yes. And then let's go ahead and see if we can graph that. Now, some of you might notice as you're looking at your table that eventually your calculator is going to do rounding for you. And sometimes the numbers are so small that they're actually going to round it to your asymptote there. And so you are just going to have to know your rules to know that it is not going to actually touch your asymptote value. Okay, so looking here, right? Wow, we're getting some really large numbers. Okay, let's see if we can just use up until here we get to 10. So maybe we would do 110, 0, 2, -1 is 1.1, -4 is 1.0. And then it looks like all of these are going to 1. Again, if you are to plug that in, okay, or even if you just go to you select this, it's technically not 1 exactly. You see this decimal here? Okay, so it's not hitting the 1, okay, but it is rounding to 1. So when you're graphing this, at 1, you're at 10, at 0, you're at 2. Okay, this is enough to get you a good picture of what's happening. And then you can see that it's getting closer and closer to the 1. Okay, so we're gonna put those arrows on there. So that one is pretty steep. Okay, and your asymptote is always what it's getting closer to. So in this case, it's not getting closer and closer to 0, it's getting closer and closer to what? Getting closer and closer to 1. Okay, so that is where your asymptote's going to be. Okay, so your domain is all their numbers. Your range is going to change. See if you can do that. Okay, the asymptote is now at y equals 1. And let's see if you can do your end behavior as well. Alright, so Lou, what'd you put for your range?
Y such that y is greater than 1.
Yes, great. And then Izzy, what'd you put for your y-intercept? Yep. Okay, and then your end behavior we're going to start with, bless you, as x goes to negative infinity. Where does f of x go? And we got to do the right side as well. Okay, so I want you to try to fill in at least one of those. Okay, and then you can think about the other part if you're unsure. Okay, so Riley, what are you thinking of for this first one here? As this goes to the left, what is f of x going towards? 1. Yep. Alright, and then Carson, what about on the other side? As we keep going to the right, where is this end going? Great. Alright, nice job, you guys. Alright. Let's try this one. Was part A growth or decay? Decay, because it's 3/4, right? Okay, so if it's approaching that asymptote, it's going to be decay. What about this one, growth or decay? Growth, because it's going to infinity. Okay. And this is negative 1/2 multiplied by 3/8, x plus 2 plus 9. Okay, what is the base for this one? 3/8, which means it has to be decay. And if it's decay, it's approaching the asymptote. Okay? Now, maybe you guys have noticed a pattern. Have you guys noticed how the asymptote changes? Do you think you could tell me what the asymptote is without the graph yet? Yep, actually close. What do you have to put with it? Not just 9, but y equals 9. Such a math teacher thing to say. Okay, so it has to be the y equals, remember, because it's an equation of the line. So again, I want you to practice plugging that into your calculator. Sometimes it might be easier if you have -1/2 to put -0.5. And then you can always use the division if you want the decimals. Okay, if you want the fractional answers, then that's okay. You can use that fraction. And with some of the calculators, if it gives you like that little caret for the exponent, then that exponent is going to have to go in parentheses. Okay, and then take a look at the table and let's pick out some values. And then once you have something in the exponent, just make sure you arrow down and put the +9 there. Then, if you know where your passing code is, if you want to put that on your graph first, you can. Hi. Yes, I will. Yep, cut. Okay, and then just keep plotting those points, and then I want you to fill those in. So this one is a reflection, okay, which is why it flipped here. We can put our arrows on both of those. So this time, because our graph flipped, your range should be y is less than. Okay, so just double check that. All the points are below 9. Okay, and y equals 9 is that asymptote. Hopefully you got your y-intercept at 8.9. Okay, and then your end behavior, you can always start with as x goes to negative infinity and as x goes to positive infinity. Okay, where do the ends go? Okay, so on this side, we know where would you say that y is going on the left side? Yep. So we're going to write negative infinity there. Okay, and then, Avian, what about the other side?
9.
Great. Okay, getting closer and closer to that. Alright, I'm going to give you your graph sheet paper, and then I'm going to put up the calendar. That way you can write it right on here.